Welcome to another episode of Learning sCrypt tutorials. In this video, I'm going to show you how to maintain state across different UTXOs using the output transaction technique we introduced earlier. So as a reminder, as we have shown before, the Bitcoin smart contract uses the so-called UTXO model. Basically, you have a output, that's a lock. You think about it, that's a lock, and in the input, to spend the coins locked in the output, you have to provide a matching key. So on a higher abstraction level, the lock can be think about as a mathematical function f, and the input can be think about as x. So only if fx equal to true, then the coins can be moved. So we already discussed that f is a Boolean mathematical function. What's the implication? There's no side effect. So doesn't matter where it's evaluated or when it's evaluated. Fx will always evaluate to the same value, regardless whether in whatever environment it is in. So this has a severe downside as people usually regard. Namely, you cannot maintain state across different UTXOs, which is not true, as we'll show. So one way to maintain state across different UTXOs in Bitcoin smart contract is to use the output transaction technique we introduced in the last tutorial. So basically, for one way to maintain state into a smart contract is to divide the lock part, the output contract itself, into two components, the code component and the state component. So the code component can be thought of something immutable that governs the state transition rules. And the state is, as the name suggests, is where we put our state that can be mutated from UTXO to the next UTXO. So basically, we carry the same code, but we mutate the state from one output to the next. So how does it look like? It looks like this. So think about, again, we have three, I think here I just draw three transactions. You can, first transaction, on the left-hand side of this vertical line is the input, as usual. On the right-hand side is the output, which is the lock part. So we divide the locking part into, as we showed earlier, code part and the state part. And when we keep calling the smart contract for this smart contract, we make sure the code part stays the same as we have seen here, while the state part can be mutated from state 0 to state 1, and then to state 2, and etc. You can keep doing this repeatedly. So the state basically transition from 0 to 1 and then to 2. So how does this look like in code? I'm going to show you one simplest example. Basically, in the state, we use a counter representing how many times this contract has been called. So let's look at, before look at the code, we can briefly review what's the SIG hash pre-image in the push transaction technique. So you can see the field 5, which is script code of the input. So basically, this is the part that you can think about the lock. This is the code plus the state part, which is the lock part. So we are going to use the fifth field. We are also going to use the hash output. So basically, this is all the outputs for the current transaction. We hash them, we concatenate them together, we hash it. This is the field 8. So let's go to the contract and see what happens here. So basically here we have a contract called counter. It has a public function called increment, and Not surprisingly, we're again using the output transaction technique. We pass in the transaction preimage and we make sure this is the correct one, meaning it's for the current transaction we are in. So once we have that, we use, as we showed earlier, we can parse the fifth field from the preimage, which gives us a script code, which is essentially the log part, meaning the code part plus the state part, and we use just 1 byte in this case to represent the counter. So it's at the very end. So we can extract using this splicing operation. We can extract the last part, which is the counter, and then we can use the counter plus 1 as a new state, and then we concatenate with the code part, which is here, which is not changed. So after that, we can put it in the new output. We require the new output contains this new script code. Basically, the code part does not change, while the state part increment by 1. We require, at the last, we require this output is what's included in the transaction image. As we showed earlier, we know from the transaction preimage, we know the hash of the outputs. So we can hash the output we specified earlier and make sure these two equal. So this in total makes sure every time we call this increment, the counter in the state is incremented exactly by 1. So if you go back, so imagine this starts at 0, so it has this part. If you run the contract, call the increment, this has to be 1 after first called, and this has to be 2 once called again, and so on and so forth. If there's anything other than 1, this will fail. So in this way, we can maintain state. Okay, I hope this is some good news for you, because it dispels the misconception that Bitcoin smart contract cannot maintain state. I hope to see you in future videos. Thank you.